Some reactions spontaneously go in one direction. For instance, if you combust wood, it doesn't spontaneously go from carbon dioxide and water back to wood. But then some are reversible. And we're going to look at those things right now. Reversible reactions we call equilibria. Okay, if you dissolve sugar in water and you put so much in that it doesn't all dissolve, what happens is the sugar continues to dissolve, but as it dissolves, some of the sugar comes out of the water and goes back into the solid. And that's an example of a reversible reaction. It can go forward and it can go backwards, and we use a double arrow as shown down here. A system may not be changing. For instance, once you dissolve lots of sugar in water and you look at it over time, you may say, but it's not changing, so no reaction is occurring. But there actually is a reaction occurring because the molecules are constantly coming in and out of that solid state. Some other examples are your bone mass isn't changing over a year's time, but your bone is constantly being broken down and being rebuilt. And so you have an equilibrium amount of bone, but there's these reactions of bone building and bone destruction all the time. So this is an equilibrium, and we can look at an equilibrium as being a balanced teeter-totter. It's nothing's happening on the surface because everything's staying equal. The concentrations of the reagents and products are staying the same even though they're being rapidly interconverted. What we're going to look at with equilibrium is what happens when you disturb that equilibrium. So this teeter-totter was at equilibrium and now we put something on it. Well, what happens is you get a new equilibrium. Okay, what about equilibrium? You see a double arrow, and this indicates that when equilibrium is established, the rate of the forward reaction is the same as the rate of the reverse reaction. Not the concentration of products and reactants, but the rate of how fast the reaction is going is the same. But once we stress that equilibrium, you change those reactions and you have a shift in the reaction one way or the other. Here's an example. Water does a teeny tiny bit of breaking apart to protons and hydroxide. This is called a proton and this is called a hydroxide. We can recognize this is an equilibrium. The way it's written, it has a double arrow. And what happens is the concentration of protons on hydroxide remains constant, even though water is constantly breaking apart and then reforming. This is a steady state. It's an equilibrium. What will affect a chemical equilibrium? Well, concentration of reactants and products, temperature, pressure, catalysts, anything that will affect the rate of reaction. So let's go ahead and look and see what happens. If we change the concentration of something in this equilibrium, like hydroxide, we add hydroxide. What happens? Well, you've increased the concentration and we say the rate of the reverse reaction increases, but just think about this. You put more of this in, it has more opportunities to collide with this, so it's going to make more water. And what happens? The concentration of the protons will go down because they're making more water. If I add protons, I have my equilibrium established and then I go and add protons, well, these can combine with hydroxide more often to form water, so hydroxide concentration goes down. Here's ammonia reacting with water to form ammonium and hydroxide. Notice the double arrow. It's an equilibrium. I add more ammonia. There's more reactions with water occurring, so the water amount of water would go down, and more of these two, ammonium and hydroxide, would be produced. Okay, right down here I'm using a shorthand. You see the bracket around the water? That means concentration of. And so this is concentration of ammonium and concentration of hydroxide. That's all that bracket means in chemistry. It actually means in a particular concentration form, molarity, but we're not going to worry about that yet. Okay, so what did we see in those two examples? When you add a component, the concentration of the other components on the same side of that reaction are consumed, so their concentration decreases. And things are made on the other side, so the concentration of the other components are increased. We'll go through many examples, or some examples on this, so you will get to practice this. If you remove something, the opposite thing happens. If I remove something, then what would react with it doesn't have as many to react with, and so the concentration of that starts building up. And less of the other side of the reaction is made, so the concentration of those decrease. Here's an example. Notice it is an equilibrium because of the double arrow. Here we have acetic acid and water. What do they make? This is called acetate, and this is called the hydronium ion. Let's look and see what happens if I add some of this. Now, the rule that we just learned is if I add something, what's with it goes down and what's opposite increases. This is called Le Chatelier's principle. So I add acetic acid, and that, as a result, the concentration of that is going to increase because I'm adding some. Now, what happens in response, a little bit of that extra is used up to react with water, okay? And then what happens is more of these two are made. So this and this also both increase. I separate this into what I am doing to the reaction, the action on the equilibrium, adding this, and the reaction of the equilibrium. This goes up. We don't ever measure the concentration of water. It's meaningless. So I don't have that in here. But the amount of this would go down and the concentration of these would go up. Okay, let's try another. You try it. Adding acetate, what happens to hydronium ion concentration and to acetic acid concentration? Well, if I add acetate right here, that's going to increase. What happens in response? I add acetate, hydronium ion goes down, and acetic acid goes up. If I add hydronium ion, what happens? Well, the concentration of hydronium ion increases, acetate decreases, and acetic acid increases. Acetate decreases, acetic acid increases. What if I remove hydronium ion? If I remove hydronium ion, the concentration of hydronium ion decreases. In response, this builds up, acetate increases, and this declines, acetic acid decreases. What if I add sodium chloride? Do you see sodium chloride anywhere in this reaction? No. So what happens in response when I add sodium chloride? Nothing. So not every change you make will have an effect on the equilibrium. It has to have a participant somewhere in that equilibrium to have an effect. Now you go ahead and look at this equilibrium and try to predict what will be the change in equilibrium when you add these things. I've changed the colors of these so you can follow what I'm saying better. We're going to be adding ammonia first. So I'm adding this reagent. What happens? Well, adding ammonia causes an increase. What's a reaction of the equilibrium? That both of these increase. If I add hydrogen, I'm increasing the amount of hydrogen. In response, the nitrogen goes down and the ammonia goes up. If I add nitrogen, what's with it goes down and what's opposite goes up. If I add nitrogen dioxide, oh, it's not in there. So what happens? No change.